All right, hello there. Today I'm going to be talking about different types of stationary points. So I want to begin by drawing the same exact graph that I had drawn in exercise 10C, which was the previous exercise. So if you guys recall, we drew a graph that kind of looked like this. Okay, kind of look like that. And we talked about how the following points, so this point over here, which we labeled as A, this point B, this point C, and this point D are all considered stationary points. So just recall that a stationary point is a point of zero gradient. Another way to think about it is if you draw a tangent line to each of those points, they will be horizontal lines, just flat. And then we spoke a little bit about how the gradient changes around those stationary points. So the gradient to the left of A is positive, and then it's 0, and then it's negative, okay? And then for B, you're going from negative to 0 to negative again. For C, we're going from negative to 0 to positive. And then for D, we're going from positive to 0 to positive, okay? So there's 4 different combinations of what's happening around the stationary point. Excuse me. So we spoke about point A is what's called a local maximum. So what's happening for a local maximum? We're going from positive to 0 to negative. Point C is what we call a local minimum. So for a local minimum, we're going from negative gradient to 0 to positive. And just recall, we call it a local maximum and a local minimum because locally, the y values are the maximum and the minimum values. And then B and D we classified as stationary points of inflection. All right, and then the key thing to consider here is that both B and D are stationary points of inflection. So as long as the gradient is the same to the left and the right of the point with 0 gradient or the stationary point, then you have a stationary point of inflection. So for example, for B, negative and negative, for D, positive and positive. Whereas for your local maximum, you go from positive to negative, and for your local minimum, you go from negative to positive. All right. So let's try some of these questions. Question 1, you've got a function. You need to find the stationary points and state their nature. So first thing, to find the stationary points, you go dy dx, differentiate, so you get 9x squared minus 16. Okay, and you know you have to set it to 0 to find your stationary points. Okay, so if this thing's equal to 0, that means that 9x squared is equal to 16, which means that x squared is equal to, divided by 9, you get 16 on 9. And that means that x is equal to, so you've got to be careful here. It's not just square root of 16 on 9. Remember, it's plus or minus square root of 16 on 9. And lucky for us, root 16 is 4, root 9 is 3. So we actually get a nice answer. You get, oh, my bad, you get 4/3 or minus 4/3. Okay? Now that's the first part of the question done. We found the stationary points. We now need to state their nature. So how do we state the nature of stationary points? I like to draw a little table that looks like this. All right. So I draw 4 lines. We have a few lines here as well. Oops, sorry. Draw a few lines here as well. Okay. So for the so we have an x value, a dy dx value, and we have the slope. Okay, so let's talk about how to fill each of these out. So what do we know? We know that 2 of the values are negative 4/3 and positive 4/3 that we're going to substitute in. What do we know? We know dy dx is 0. So we know the slope for both these things are 0 gradient. So they just look flat like that. All right, now we know these are the only two stationary points, which means the gradients to the left and to the right have to be consistent because there's no way to go from negative to positive or from positive to negative unless there is a local maximum or local minimum there. So that means that the gradient in this region, and this region over here are all going to be the same. And what are these regions? Well, we just have to choose a point. For example, for negative 4/3, we just have to choose any point to the left of that and any point to the right of that. But you got to be careful with this point over here. You want it to be specifically between negative 4/3 and positive 4/3. So I'll just write in red. We want to choose a point for this one that's less than negative 4/3. We want to choose a point for this one that's between negative 4/3 and 4/3. And we want to choose a point for this one that's greater than 4/3. Because the gradient cannot change in those regions because there are no stationary points there because we found all our stationary points, which means that if we just evaluate the dy dx at any of those points, it'll tell us what the slope looks like. So just for argument's sake, I'm going to choose -2, 0, and 2. So I'm just looking for simple values to plug into dy dx. So we know that dy dx is 9x squared minus 16. So if you sub in -2, you get 9 times 4 minus 16, right? Which is greater than 0. All right, so I'm just going to put a positive in there. Now, if you put in 0, you get 9 times 0 minus 16, which is greater than 0. Less than 0. So you put a negative in there. And for positive 2, 9 times 4 minus 16, which is greater than 0. So you're going to put a positive in there. So the slopes would look like this, and hopefully this shape is kind of familiar if you piece everything together, right? Because you've got a cubic function which has a positive coefficient for x cubed, which means that you already know the shape for a cubic function would look like that. So we expect the turning point to the left to be a local max, the turning point to the right to be a local min, and that is consistent with what we see for our slope. So what can we conclude? At x equals -4/3, we're talking about this behavior here. Oh, my bad. We're talking about this behavior, which corresponds to a local maximum. And similarly, for x equals 4/3, we're talking about this behavior, 4/3. We're talking about this behavior, which corresponds to a local minimum. And that's exactly how you find the nature of stationary points. Just sub in a point to the left, to the right, check what dy dx is, and it'll tell you straight away. And now it's asking you to sketch the graph. We have made pretty light work of part A, and now we just have to use our information from part A to help us for part B. So just remember, if we're sketching this graph, right, we're also going to have to know x-intercepts. We've got turning points. We're going to have to know x-intercepts as well. So it's a little bit tricky, this one, because it's going to require us to solve for x-intercepts, which, because it's a cubic, it's not necessarily easy to do. But what I can do is try and graph it the best I can. So we know that there's a point at -4/3, a stationary point at -4/3 and a stationary point at 4/3. So if you do y of -4/3, you get that that's equal to, I might put this into my CAS. Give me one moment. So you define it on your CAS. -16 times x plus 2. And I might just see what that function is at -4/3. You get 146 online. So I know these questions aren't usually designed to be CAS questions, but just in the interest of time and also the fact that the values aren't really nice, I'm just using my CAS to find these values. Obviously, these are something you can find directly by hand. It just takes more time. So y of 4/3 is negative 110 on 9. And now the other thing that you might want to do, for example, is to factorize the rule. However, it doesn't look like it's got a nice factorized form. So what do we end up getting? We end up getting negative 4/3 146 on 9, which might be here. 4/3 negative 110 on 9, which might be here. And you get a graph that kind of goes through that. So overall, we've got something. Oh, my bad. Just got to be careful because you do know the y-intercept is 2 from the graph. So you got to try and incorporate that the best you can. Okay, and to label your key features here. So this point over here is negative 4/3 and 146 on 9. This point over here is positive 4/3, negative 110 on 9. This point over here is 0, 2. And then to find your x-intercepts, that could just be another solve on the CAS. So again, I know if we were using our CAS, we could just graph this directly. But the key idea for questions like this is that you wouldn't usually get something that's pretty nasty to factorize. So I'm just going to put it into my CAS and see what it gives me. So f1 of x equals 0 for x. Yeah, so it has an answer. They're just not nice answers. So I'm going to put these correct to 2 decimal places. So this is like negative 2.370. This one over here is 0.130. And this one over here is 2.240. Okay? So this is an example of a question where I did need a CAS to get all that information, but I can assure you that not every question is going to be like that, okay? So question 2 explicitly says we're going to use a CAS for it. So I will just define it on your CAS. So I'm going to do f2 of x equals this function, so x cubed minus 14 times x minus 3. And I'm hoping while you're watching this video in class, you're also typing this into your CAS and doing the questions with me. So the first question is the value of y when x equals 3. You just do sub in x equals 3 and you end up getting one second, sorry. So you sub in x equals 3 and you end up getting negative 18. So let's go back to black. When x equals 3, y equals negative 18. And you can verify that yourself, but because it's a CAS question, I just put it in my CAS. So for part B, we want to solve x cubed minus 14x minus 3 equals 0 for x. And we end up getting, I'll tell you in a second. Let's just do it. You end up getting really disgusting answers again. But again, we're going to do correct to 2 decimal places. So let me make that note. Correct to 2 decimal places. And we end up getting x equals minus 3.63, minus 0.21, and 3.84. Okay? Now the value of dy dx when x is equal to 1. So on your CAS, if you go menu, calculus 4, and you can differentiate at a point. So number 2, derivative at a point. So variable x value 1, because you want to do it at x equals 1. Press enter. and then it asks you to input your function. So you just put f2 of x or whatever you've called it on your calculator, and it gives you the answer straight away. So on your calculator, it'll look like d dx of, oh, my bad, of f of x evaluated at x equals 1 equals minus 11. So that's the gradient at x equals 1 of that graph. And then the last part is the coordinates of the local maximum. So for this one, I think it's best to get a graphing page out and to graph f2 of x, or whatever you've called it on your CAS. I've called it f2 of x. All right. So I'm just in the process of getting that done. Sorry, 1 second. All right, so if I go menu, so a good way to get the right fit if your fit's not good, you go menu, 4 window zoom, and you can do A, which is a zoom fit. It's not always perfect, but it usually gives you something you can work with at least. And then if you go menu 6 analyze graph, you can find minimums and maximums. This is a cubic which only has one maximum, and it wants you to find the coordinate. So if I kind of just, 1 second. If I kind of just use that maximum, it gives me negative 2.16 and 17.2. So these don't seem to have very nice answers, which is fine. That's going to happen sometimes. All right. So question 3 wants you to sketch the graph of e to the power of x cubed. So we need to use a combination of stationary points here as well as limiting features. So I'm going to talk about that a little bit now. So what do we know? We know that f dash of x equals chain rule. So you get 3x squared e to the x cubed, and that's equal to 0 for stationary points, okay? So when's this thing equal to 0? Well, either 3x squared is equal to 0 or e to the x cubed is equal to 0. The first one tells you that x has to equal 0. The second one, e to what power gives you 0? If you think about it, as the power gets smaller and smaller, it gets closer to 0, but there's no actual number that gives you 0. So you only get your one solution, which is x equals 0, is your stationary point. And f of 0 is e to the power of 0 cubed, which is just 1. So you have a stationary point at the value 0, 1. And now the other interesting thing that we might want to consider is as x gets larger and larger, e to the x cubed gets larger and larger. And as x gets, so we can say, as x approaches infinity, f of x also approaches infinity. And as x approaches minus infinity, so think about larger and larger negative numbers, then we would get larger and larger. So we get e to the power of larger and larger negative numbers, and you know that that gets closer and closer to 0. So you get this kind of behavior happening. So we know because it can never be less than 0, there has to be an asymptote at y equals 0. So I'm going to draw that with a red dotted line. So there's an asymptote at y equals 0. There's a stationary point at x equals 0. And our graph, well, actually, we should actually try and find the nature of the stationary point. So you can tell straight away that 3x squared is always, so I'm having a look over here, this thing over here, all right? 3x squared is always greater than 0 for any x, and e to the x cubed is always greater than 0 for any x, right? So it doesn't matter what x value you plug in there, this thing always has a positive gradient. That is the key thing that you need to know here. So always has f dash of x greater than 0 for all x, since 3x squared greater than 0 and also e to the x cubed is greater than 0. Okay, so both those things are true, which means you always has a positive gradient. So your graph, if you know that this point over here is 0, 1, okay, and you always have a positive gradient, it has to look like this. Okay, so this has all the features of a graph that we need to include, which is when x goes to minus infinity, the graph goes to 0. When x goes to infinity, the graph shoots off to infinity. So this behavior, and you have your stationary point at 0, 1. And more specifically, we know it's a stationary point of inflection since the gradient to the left and the right must both be positive. All right, question 4, last one. So we got our graph, which is x log e of x. Part A is find f dash of x. We need to use the product rule. So we get f dash of x is equal to u. So x times derivative of log e of x, which is x times 1 on x, plus log e of x times derivative of x. So you just get log e of x by itself because derivative of x is 1. So you end up getting 1 plus log e of x. Now, part B wants you to solve the equation f of x equals 0. So that's the original equation. So we want to solve x log e of x equals 0. So null factor law, either x equals 0 or log e of x equals 0. So if log e of x equals 0, that means that x has to equal e to the 0 using your log laws, which is 1. All right, so x is either 0 or 1. Now, solve the equation f dash of x equals 0. So we're solving 1 plus log e of x equals 0, which means that log e of x equals minus 1, which means that x has to equal e to the power of minus 1. Now, if you think about that, e to the power of minus 1 is some number between 0 and 1. Okay, so now last part is to sketch the graph. I guess one thing you need to think about is the domain is 0 to infinity, okay? So what would the graph kind of look like, potentially? I'm only going to show the positive half of the graph, y and x. So we know it has x-intercepts at 0 and 1, which are here and here. We also know it has a stationary point at 1 on e, which is roughly around a half. So how do we know what's the nature of the stationary point? Well, we can just sub in 1 point to the left and 1 point to the right of e to the minus 1. So let's do the nature of the stationary points test. So we've got 0, e to the minus 1, 1. So you know the slope at e to the minus 1 is 0. If you sub in 0 into f dash of x, you get 1 plus log e of 0, which is 1 plus 1. Oh, no, sorry. If you sub in 0... Oh, hold on a second. Give me 1 sec to think about this. 0 itself is not defined, right? So going back to part B, this is not defined. So your only answer is actually at x equals 1. I didn't recognize that. So let's go back to... So the reason 0 is not defined is because this is your domain. So on that note, let me get rid of that. And let's go back to thinking about what's happening at e to the minus 1. So we can't choose 0 anymore. But we can choose, for example, a third, which is definitely less than 1 on e. Okay, so if we sub in a third, we get 1 plus log e of a third. So it would probably be a little bit tricky to figure out exactly what that is without a CAS. So let me just get an approximation for it. 1 plus log e of a third. I think it's going to be negative. It is negative. So you know you get that it's negative slope here. And then for 1, you get 1 plus log e of 1. Log e of 1 is 0, so that's positive. So what do we have? We have a local minimum at the point e to the minus 1, and we have an x-intercept at the point x equals 1. So if that's x equals 1, e to the minus 1 has to sit underneath it because it's a local minimum. Maybe there. And then it's an open circle at x equals 0 because it's not defined there. But it's kind of going to look like this, okay? So the key points here are, this is e to the minus 1, and then well, really, we have to find the y value as well, yeah? So f of e to the minus 1 equals e to the minus 1 times log e to the minus 1 equals minus e to the minus 1. So let me plug that in. All right, this point over here is 1, 0. And that's probably all the information we need anyway to sketch the graph. All right. So I'm going to finish up there. Thank you for listening. Please do the questions at the bottom and hope you have a nice day.